Hi, I'm very happy to be here to talk about video surveillance networks. My name is Claire Vacherot. I'm a pentester and researcher at Orange Cyberdéfense in France. And my specialty is penetration testing OT systems, and more generally, not IT, including video surveillance networks. So these systems involve the devices, the components that are used to capture, display, record, store, or whatever, a video stream. And this stream can be used, for instance, to monitor a process or part of a process, but most of the time they are used to monitor and detect intrusions within or around the facility. So compromising them is usually a matter of safety and security as well. There are, of course, different types of video surveillance systems, including different types of devices, depending on the functions. And different types of systems can interact using different means, but here we are going to focus on only one, on IP-based video surveillance systems, and more specifically, the one that comply with the ONVIF standard, which is actually the main standard for this purpose. Okay, so here we are doing a penetration testing assessment. So when we are in this situation, we usually start by plugging on a customer's internal network. And most of the time, we are starting from the user VLAN. And from there, either we unexpectedly start encountering video surveillance components, or we can also actively look for them. So pen testers, including me, of course, usually know how to interact with this device, but they do not always use specific components of these services and specific functions of these devices. So we are used to use standard IT services such as the web interface, the FTP, the SSH, and so on. So first, we are going to talk about some of these specificities and see how we can use them to better discover and interact with these systems. And this will lead us to the video stream itself, which is the center of these systems and, of course, of this presentation. When I started this research, what I wanted to do was to see how we could do the attack where you intercept a video stream and replace it with somewhere else. I wanted to see how it could apply to pentest. And when I did that, I discovered that, of course, there are many well-known attacks and so on, but I discovered that they rely on prerequisites that are not met most of the time during pentest. So we are going to see how to overcome as much as possible this difficulty and hopefully make the attack work. And you may not see, but on stage there's a live demo. So I guess it's time to start praying for the demo gods. OK, so first, let's find our network surveillance components. So during an assessment, unless we have been given a map of the network, we don't know where these components are, so we'll start looking for them. But whether we will or not find them depends on how the network is organized, of course. If it follows the state of the art, we should never be able to see video surveillance component from a user VLAN, because then it should be in a dedicated and segmented network zone. But you can imagine that this is usually not what we see. It's very common that they are mixed with other types of components covering other functions. For instance, it can be mixed with OT, building management systems, safety, such as access control, things like that. And by mixed, I mean either on the same VLANs or different VLANs, but no segmentation, and so on. OK, so I see this a lot, but the thing I see the most is this configuration, where video surveillance components are mixed with everything else. So this means that from our starting position in the user VLAN, we already have a direct access to them. So this is what we are considering here in this demo, of course. Another thing I want to mention briefly about network organization is that these systems, these networks must also be segmented internally by trust zone, for instance, what's inside from what's outside in public zones, by type of components, and so on. But I've only seen this once, and usually everything is just mixed once again. So since if you reach one of these components, you reach them all. So again, this is a situation we are considering here. OK, so how do we find our devices? Well, the most obvious way is direct unicast network scans using Nmap, targeting standard IT protocols and specific protocols such as RTSP, which I'll talk about later. But yeah, you know that. That's not very OPSEC. Another thing that works fine with on-VIF components is that many of them understand zero-conf protocols, at least one zero-conf protocols. So this is a very useful way to discover this kind of devices. Just to show you, I have written a small Python script that does zero-conf discovery using SSDP and WS discovery, which are two zero-conf protocols. So I'm going to show it to you, and it will allow me to introduce the setup first here. So, OK. So we are trying to make sure that nothing happens to this piggy bank. So that's why there is a camera pointing at it. I'm trying not to think people, sorry. So this is our main camera. I also have a security guard station, so that the security guard, the viewer station, so that the security guard makes sure that nothing happens to the piggy bank. OK, just one moment. It won't stay in place. OK. Right. OK. So all of these are on the network. I also have, on the same network, my attack laptop, of course. And I have an additional virtual server for network things and with video management software as well. So as I said, I will run my script. What it does is that it will send a few multicast requests for SSDP to discover different types of devices. It will do the same thing for with WS discovery. WS discovery is web service discovery, by the way. And we can see that we have a few results. So this one is our server, the virtual one. This one is the Axis camera, which I used to present the setup. And this one is the main camera, which is a Pelco, and which is the main camera monitoring the piggy bank. OK, so with this means that we have already discovered all video surveillance-related components on this small network. So it works fine. It has good result during penetration tests. The only quite big limitation can be that it works only if multicast is rooted, of course. OK, so that was for the introduction, in a way. So now that we have discovered these devices, we will try to access it. These devices have management services, like we are used to, like web interfaces, FTP, and so on. I'm not really getting into details here. You know how it works. It has common flaws, as usual, default or weak credentials, and encrypted protocols. They can have vulnerabilities that can be exploited, and so on. An interesting service for management is this one, is the on-VIF web service. It's used by OnVIF supporting software to gather information and to configure OnVIF devices. So this one can be pretty useful during a pen test to have information on a device. It requires credentials, normally, but I've seen it unencrypted, so it may work this way. So to show you, once again, briefly how it works, I have written another small script that does a few GET requests on the cameras. I only do GET requests, a few basic GET requests with information required during pen test. There are many other things to get. And I did not do any set requests because during penetration tests, we try not to break our customer's environment by randomly changing settings. So I'm not doing this. So we will run it on one of the camera. This one is use HTTPS, which is a good practice. And I set myself these credentials to stick to the reality. And you can see that we have quite a few information. I will run it also on the other camera. This one is not encrypted. This is the default credentials, but the camera is older, but that's why. Let's say this is why, at least. So this one takes longer, but we'll get back to it later with the details. OK, so this is for the management services, but we are mostly here to see the video itself. So we can view it usually from the web interface. There's usually a live view. But the main protocol that is used in OnVIF environments is to transmit the video is the protocol RTSP, usually on port 554 TCP. How does it work? So when a device wants to retrieve the video of a capturing device, such as a camera, it will initiate a session to this camera using RTSP. And in return, the camera will send the video data in a network stream. And this protocol is unencrypted. So everything goes in clear text. There is an encrypted version of the protocol, or several, maybe. But I've never seen them implemented in real life so far, so, well, we won't do that. Just to show you how it works, for those who are not familiar with this, we can just use any media player, and we will open a network stream. And we can read it. So, as you can see, this requires credentials as well. And then we can view the live stream here. Right. OK. So, as you can see, it requires RTSP. Again, I've seen it unauthenticated quite often. It can also have default or re-credentials, and these credentials can be brute force. For instance, there is this very useful tool called Camera Radar that can brute force RTSP credentials. By the way, RTSP, the authentication mechanism for RTSP and the OnVIF web service are not the same, so the credentials can be different, and it's not because the authentication is enabled on one side that it's enabled on the other side. OK, one other thing you might have noticed is that when I access the RTSP stream from VLC, I use a special path to access it, which is called a stream URI. And this one can be quite painful to find during penetration tests because it can be different depending on the vendors and the models, the configuration, and so on. So it's not very easy to find. So I use the first one. The second one is for the other camera. And I put some other examples of stream URI you can find. So basically, it's like credential. It's hard to find like credentials, or not hard, depending on the configuration, of course. How do we get it? So the legitimate way to do it is by using the OnVIF web service. if you have noticed, when I did the on-viv discovery, I retrieved this information. So this is the right way to do it and the easiest way. But of course, you need to have the on-viv web service credentials. We can also find sometimes the stream URIs in user manual, but not that often because users are not supposed to know this information because they are supposed to use the software to access it. There are also very big online databases with a lot of stream URIs that can be used. And finally, for simpler paths, the tool camera that brute force RTSP credentials can also brute force RTSP stream URI. OK, so now we know how to access the video stream legitimately. But let's see what more we can do, of course. Oh, yeah, first I wanted to show you this. So do what you want with this information, as long as it's legal and ethical. And you should also unplug your own surveillance systems, by the way, if you maybe. OK, so what we are doing now, what we just did, is we initiate a session with a camera using the credentials. It's independent from all other sessions established with that same camera. We can establish many sessions. And the only thing we can do is retrieve video streams. So that's good, but can do better than that. If we instead intercept a legitimate video stream running between a camera and a viewer, we have two benefits. The first thing is that we don't need to know the RTSP credentials and the RTSP stream URI because the traffic goes through our laptop, and it's encrypted, so we see the video data already. So that's interesting. And the other thing is that since we see the video stream, we can also modify it. Yes, the only thing is that since we are doing network attacks and tampering with video streams for security, it can have a quite important impact on availability, traceability, safety. So it must never be done in a sensitive environment. But here we're not in a sensitive environment, of course, so we are doing it. What we will do next is we will first intercept the video stream. Then we will see how we can view the intercepted stream on our attack laptop. And spoiler, this is the most difficult part. And finally, we will see how we can tamper with the video stream. What we will try to do here is to do the looping trick, meaning that we will record a sequence, a video sequence, and then we will replay that same sequence in a loop and send it to the viewer instead of the legitimate stream. You probably have heard about this technique. It's quite well known. It has some history. You may have seen it in movies, first of all. This one is very nice. But, well, it's a movie, so they did not really care about the technical details. 10 years ago, Van Albert and Banks demonstrated it at DEF CON. They used a physical device that was plugged directly on the Ethernet wire. It gives amazing results, but it's quite hard to reproduce during a penetration testing assessment. Myself, I have written a tool a few years ago to do that with my colleague Nicolas, but it's not that good, so it's not public. And also, you can find tutorials online or in books that can have this kind of technique or other techniques targeting RTSP. And I like this one. It's a very good one in the book Practical IoT Hacking. But my tool or any tutorials I've seen online, none of them can be used during a penetration test. And I will explain why in a few minutes. But first, we will intercept the video stream. This is really the easy part. You can use any man-in-the-middle technique and tool you are familiar with. Here, I just stick to the basics. I do ARP poisoning with EtherCap. So I will do it between the Pelco, the main camera, and the viewer. And I must mention that I used a Pelco and an Axis camera, but what I'm doing here is completely independent from the vendor, so it's not a matter of a vendor. Okay, so we can see that there are a lot of things going through us. This is actually the video data, but it's not very practical having it this way. So, of course, the next step will be to transform that into a video. So, there are probably several ways to do it, but what I chose to do was this solution. So I intercept the stream. When it's on my laptop, I will duplicate it. I will forward the original stream to the destination so that the viewer does not know I am currently intercepting the traffic. And in the meantime, the duplicated traffic is redirected locally on a local socket so that I can open the stream arriving on that local socket from my media player. Okay, so of course, I wrote a tool to do that. Unlike the previous one, it's not in Python, but in C, because Python is not, say, optimized enough to handle the bandwidth of a video stream. And also, I like C. Okay, so we'll do that. Is the stream still up? Yes, very good. So I will need just a quick information. I keep the destination port so that I can just filter on this port to make sure I get only the video stream. And also, I use the same port as a local stream, as a local socket, for the local socket, sorry. And now I will run my script. So, between my Pelco still, filming the piggy bank, the viewer, on this port, I use the mode redirect, and this option is to tell it to do the man-in-the-middle attack directly in the program so that I don't have to run EtherCap on the side. So what does it say? It says that packets will be redirected locally on this port. We can check that. It's better. That's me. Yes, we see that there are things arriving. So this means that we may be able to open it. What port was that already? I don't remember. OK. But, so, it loads, but it will keep on loading and never open anything. And that's normal. This is because how RTSP works. So when you actually initialize a session with using RTSP, before sending the video stream itself, the camera or capturing device will send the information required for the viewer to understand the stream and to be able to transform the data into a video. So this includes the video format, resolution, frame rates, and many, many other parameters. So it looks like this. This information is carried in a special RTSP frame. It's in a format called SDP for Session Description Protocol. It looks like this. And by the way, you can also export it as a file and feed it directly to the media player. So this SDP thing is the reason why we cannot use the previous tools to do what we are trying to do during penetration tests. So the tool I wrote a few years ago does not work if we do not catch the RTSP session initialization, including this SDP information. The good tutorial I like from practical IoT hacking also captures this RTSP session in it. But here we are on a pentest, and we are testing systems normally that are running 24 hours a day. So probably the sessions we are targeting have been established long before we arrived. So there's very low chances that we will see this SDP and any other RTSP info session. So what do we do then? We still need it. So there are a few ways to retrieve it. So we can try them depending on the situation. The most straightforward way is to initialize another RTSP session, an independent one, with the camera. We retrieve the SDP, and then we can use the same SDP on our intercepted session. It works. Another thing is, well, I read in the RFC that special blocks can be sometimes included in the frames carrying the video data. And these blocks would include the video information. But none of my 4 test cameras from different vendors implemented it, so this is theory, just, I don't know. And the last thing I could think of is to forge a SDP file, to create one from scratch. It could be possible for standard formats, such as MPEG, but the standard I meet the most are H.264 and H.265, and this one include additional parameters. You can see, for instance, this very weird string at the end. It's generated from a combination of many, many parameters. So in theory, you could forge one, but there are low chances to find the exact set of parameters that would match a specific video configuration. But still worth trying. So here, we won't do that. So we will just establish another session with the camera and retrieve the SDP as a file. So of course, there's a tool for that. Once again. Up. Oh, come on. Sorry. OK, so it looks like this. I will just need to do one additional change to this. I need to tell it where to read from locally. So I set the port. And if everything goes well, I should be able to open the stream. It's demo, of course. So apparently it does not. Did I mess with the port? Sorry? Ah, that's why. OK. That's unexpected. And of course, the session is down, so OK. Back on. Sorry for that. Hopefully, we have time. So now there's a new port, so I need to change it. And it works. Thank you. OK, so that's one part of it. I'm not done. There's still one chance to fail. OK, so now we catch the video. We see the video locally, but we don't tamper with it. So this is what we'll do next. So the idea is very simple. We record a sequence first, and then we will replay that sequence. This is what we will send to the viewer. Technically speaking, RTSP is in fact a combination of 3 protocols. There is RTSP for session management and for to control the video, like play, pause, and so on. There's RTCP that sends regular checks about the video. And the video data itself is carried in RTP frames. So this means that technically here, recording a sequence of video actually means recording a sequence of RTP frames. So this is what we will do. But of course, it's not just as easy as just recording a bunch of frames and then sending the same frames over and over again to the destination. RTCP is normally on UDP, and so that the media player knows in which order to read the frames, there are the sequence number and the timestamp carried in each RTP frame. So if we just send the RTP frames over and over again as is, of course, at some point, the timestamp and the sequence number will go back in the past, the stream will become inconsistent, so the video stream will stop on the media player. So it's not a very big issue, but still we have to overcome it. There's probably several probability, but what I chose to do was to keep the header of new RTP frames coming on my laptop, arriving from the camera. So I'm keeping the latest RTP frames header, and I'm just replacing the content of the video data with the one I recorded previously. Now it's demo time. Is it running still? Yes, good news. So first, I will need to end the previous attack. And I will use the exact same script, but this time I will use the mode replace, and I chose to record this amount of frames. This may have side effects because there is a lot of lights on stage, so it depends. So we will see what it does. So currently, as you can see, it's recording the stream to be viewed later. And yeah, now it's done. So it should be replacing currently the video stream with what we have recorded previously. So now, I don't know for now, but the attack should work. It's just that I don't see it. So this means that we don't need to care about all the SDP thing. I will just open it, of course, so that we can see what's going on. Right. And at the same time, I will open the other camera stream so that people who do not see the viewer workstation know what's going on the viewer workstation. OK, and now, if everything goes according to plan, I should be able to steal my own piggy bank. Thank you. I'm as surprised as you that it worked. So OK, so that's it. A quick word about the remediation, of course. The best remediation I can think of is network segmentation. It's better if no unauthorized user can reach these, let's say, critical systems. It's also better if the credentials are not admin-admin. So harden your configuration, enable security features when there are, of course. And it's also better to upgrade to the secure version of RTSP, but I know that it raises compatibility issues with other devices on these systems that are older, and that's why I've never seen them implemented. I've never seen it implemented so far. Okay, so to conclude, as you can see, targeting this system requires some knowledge, but technically it's okay, right? So the tools that I have used during this presentation are now available on Orange Cyber Defense's GitHub page. Of course, I'm French, so the name is kind of French. So feel free to use these tools, only to make the world a better place, of course. And feel free to improve them as well. There are other things that can be done with that, or the attack can be improved, I'm sure. I have mentioned several other leads, things to do during this presentation. There are more. So I will be very happy to talk about it with you after the conference. And yeah, thank you. It's still there.
Hello. Yeah, thank you for the great presentation. I was just curious about to mitigate this issue. Where do you consider, or who is responsible for this? Is the manufacturers? Is there something they can do, or is it more of an implementation customer?
Well, the manufacturers need to provide this still because it's standard, and at least for compatibility. And there are older material relying on this. So since this is a standard, I don't think this is the manufacturer's problem, but more of an implementation problem, because more recent devices tend to implement the secure version.
Okay, thanks.
You're welcome.
Yes, thank you for a great presentation. I was wondering a bit about the reconnaissance part and the zero configuration stuff you did in the beginning to discover the devices. How noisy is that? Is that something the SOC team would discover?
For the discovery, it's not very noisy because it's multicast. So I think in total it should be, since I'm sending like 4 or 5 requests for each protocol, targeting different types of devices, it's 10, but we can go down to 1 or 2. Well, 1 for each protocol here.
All right, thank you.
So not very noisy, but multicast, I guess it's not very noisy. And I don't often see it in detection rules for network discovery. But I may be wrong, but I've never seen it so far.
Thank you.
Thank you.